Today we are going to talk about polynomial rings. First, the definition. If R is a commutative ring, the set of formal symbols R of x equal to an x raised to n plus an minus 1 x raised to n minus 1 and so on up to a1x plus a0, where ai belongs to R and n is a non-negative integer, is called the ring of polynomials over R in indeterminate x. Two elements an x raised to n plus an minus 1 x raised to n minus 1 and so on up to a1x plus a0 and bm x raised to m plus bm minus 1 x raised to m minus 1 and so on up to b1x plus b0 of r of x are considered equal if and only if ai is equal to bi for all non-negative integers I. Define ai is equal to 0 when I is greater than n and bi is equal to 0 when I is greater than m. Now we define addition and multiplication as follows. Let R be a commutative ring and f of x and g of x be two polynomials over R of degrees n and m respectively, that is f of x is a n x raised to n and so on up to a0 and g of x is bm x raised to m plus so on up to b0. Then f of x plus g of x is equal to as plus bs x raised to s plus as minus 1 plus bs minus 1 into x raised to s minus 1 and so on up to a0 plus b0. In other words, we are adding term by term, where s is the maximum of m and n. ai is 0 for I is greater than n and bi is 0 for I greater than m. Also, f of x into g of x is equal to cm plus n x raised to m plus n plus cm plus n minus 1 x raised to m plus n minus 1 and so on up to c1x plus c0, where ck is ak b0 plus ak minus 1 b1 and so on up to a0 bk for k equal to 0, 1, 2 up to m plus n. If f of x is an x raised to n plus an minus 1 x raised to n minus 1 and so on up to a1x plus a0, where an is not equal to 0, we say that f of x has degree n. The term an is called the leading coefficient of f of x, and if the leading coefficient is the multiplicative identity element of R, we say that f of x is a monic polynomial. The polynomial f of x equal to 0 has no degree. Polynomials of the form f of x equal to a0 are called constants. We usually write f of x is n, degree of f of x is equal to n to indicate that f of x has degree n. Again, we use the conventions that we have with polynomials with real coefficients. We adopt the following. We can insert or delete terms of the form 0 into x raised to k. 1 into x raised to k we simply denote as x raised to k. 1 into minus ak x raised to k will be denoted as minus ak x raised to k. The next theorem says that if D is an integral domain, then d of x is an integral domain. Let's go through the proof. It's easy to verify that d of x is a ring. We can easily verify all the properties of the ring for d of x. They come directly from the properties of d. And again, d of x is commutative whenever d is commutative. Now if I take 1 to be the unity element of d, that is the multiplicative inverse identity, we can see that f of x equal to 1 is a multiplicative identity of d of x also. Now suppose I take f of x equal to an x raised to n and so on up to a0 and g of x as bm x raised to m plus bm minus 1 x raised to m minus 1 and so on up to b0, where an is not equal to 0 and bm is not equal to 0. Then by definition f of x into g of x has leading coefficient an into bm, and I know that d is an integral domain, and since an and bm are not equal to 0, an into bm is also not equal to 0. Next we come to the division algorithm for f of x. Suppose f is a field and I have two polynomials f of x and g of x over f with g of x greater than or equal to 0. Then I can find unique polynomials q of x, r of x in f of x, capital F of x, such that f of x is equal to g of x into q of x plus r of x, and either r of x is equal to 0 or degree of r of x is less than degree of g of x. We have two parts to this proof. First the existence and then the uniqueness. So proof of existence. If f of x is 0 or degree of f of x is less than degree of g of x, we simply set q of x as 0 and r of x equal to f of x. So let me assume that degree of f of x, which we are going to call as n, is greater than degree of g of x, which I take as m. And suppose f of x is a n x raised to n plus a n minus 1 x raised to n minus 1 and so on up to a naught, and g of x as usual is bm x raised to m and so on up to b naught. Now I define f1 of x like this. f1 of x is f of x minus a n into bm minus 1, bm raised to minus 1, x raised to n minus 1, n minus m, g of x. Now obviously the first term gets cancelled because an into bm minus 1 into bm x raised to m into x raised to n minus m is going to be exactly equal to an x raised to n. So this term with degree n gets cancelled, and hence the coefficient of x raised to n is 0 in f1 of x. So definitely f1 of x has degree less than or equal to f of x. So either f1 of x is 0 or degree of f1 of x is less than or equal to degree of f of x. By the induction hypothesis, there exists q1 of x and r1 of x, which are polynomials in over f, such that f1 of x is equal to g of x into q1 of x plus r1 of x, where r1 of x is 0 or degree of r1 of x is less than degree of g of x. Then I can write f of x as a n bm minus 1 x raised to n minus m g of x plus f1 of x. This is from the definition of f1 of x. And then what I do in the next step is write f1 of x in terms of the quotient and remainder when divided by g of x, and so I get this expression. In the next step I take the g of x common out and say this is equal to a n bm minus 1 x raised to n minus m plus q1 x into g of x plus r1 of x. Now at this stage I have something into g of x plus a remainder, and this expression inside the bracket I take as q of x. This r1 of x I take as r of x, and these two satisfy the required properties, and hence we have proved the existence. Now let's prove the uniqueness. Suppose I can write this in two ways, that is f of x can be written as g of x into q1 of x plus r1 of x, and can also be written as g of x into q2 of x plus r2 of x, where r1 of x is 0 or degree of r1 of x is less than degree of g of x, and again r2 of x has the same property. Now when you subtract, I get 0 is equal to g of x into q1 of x minus q2 of x plus r1 of x minus r2 of x. Now I take the r1 and r2 onto the other side of the equation, so I get r2 of x minus r1 of x is equal to g of x into q1 of x minus q2 of x. Therefore r2 of x minus r1 of x is 0, or the degree of r2 of x minus r1 of x is at least that of g of x. Now I know that that is not possible, and therefore r2 of x is equal to r1 of x and q1 of x is equal to q2 of x. Now a little more terminology. Let D be an integral domain. If f of x, g of x are polynomials over D, we say that g of x divides f of x in d of x, and we write g of x slash f of x. If I can find the h of x such that f of x is equal to g of x into h of x. In that case, we also call g of x a factor of f of x. An element a is a 0 or a root of a polynomial f of x if f of a is equal to 0. When f is a field, a is an element of f and small f of x is a polynomial over f, then we say a is a 0 of multiplicity k if x minus a raised to k is a factor of f of x, but x minus a raised to k plus 1 is not a factor of f of x. Now we come to the corollaries of the division algorithm. First, suppose f is a field, a is an element in f, and I have a polynomial f of x over f. Then f of a is the remainder in the division of f of x by x minus a. Coming to the proof, by the division algorithm we can find polynomials f of x. Given polynomials f of x g of x, we can find q of x and r of x such that f of x is g of x into q of x plus r of x, and either r of x is 0 or degree of r of x is less than degree of g of x. If g of x is equal to x minus a, then r of x is a constant because degree of x minus a is 1, so therefore degree of r of x should be less than that, and therefore it has got to be a constant. Hence f of x is equal to x minus a into q of x plus r. Setting x equal to a, we get f of a is equal to r. Hence f of a is the remainder in the division of f of x by x minus a. Next, suppose f is a field, a is an element in f, and f of x is a polynomial over f. Then a is a 0 of f of x if and only if x minus a is a factor of f of x. By the remainder theorem, x minus a into q of x plus f of a is f of x. Since x minus a is a factor of f of x, the remainder on division by x minus a should be 0. Therefore f of a is 0. Third corollary it talks about a number of zeros of a polynomial. A polynomial of degree n over a field has at most n zeros counting multiplicity. This we prove by induction on n. Now, clearly a polynomial of degree 0 over a field has no zeros. Now suppose f of x is a polynomial of degree n over a field and a is a 0 of f of x of multiplicity k. Then f of x is equal to x minus a raised to k into q of x, and q of a is not equal to 0. Since n, which is the degree of f of x, is equal to degree of x minus a raised to k into q of x is equal to k plus degree of q of x, we have k is less than or equal to n. If f of x has no zeros other than a, we are done. On the other hand, if b is not equal to a and b is a 0 of f of x, then f of b is 0 and it's equal to b minus a raised to k into q of b. So b is also 0 of q of x with the same multiplicity as it has for f of x. By the principle of mathematical induction, we know that q of x has at most q of x equal to n minus k zeros counting multiplicity. Therefore, f of x has at most k plus n minus k, which is equal to n zeros counting multiplicity.